In the next section of your book talks about using capacitors in series and parallel circuit elements. But let's take a step back and talk about a general circuit first and how capacitor is used in a simple circuit. So, a capacitor we're going to look at in a direct current or DC circuit. Now, DC means direct current. Batteries are DC sources. A lot of generators, motors can be DC motors. Your cell phone, your laptop, all charge and use direct current in the infrastructure of that device. However, household appliances use alternating current or AC current. So alternating current, the voltage changes with time, whereas in direct current, it does not. If you've ever wondered why you have to use a little adapter when you plug in your cell phone or your tablet or your laptop into the wall, unlike a lamp, which is just a simple cord, you have usually a brick, a power brick. Some are tiny for cell phones, others for gaming devices or electronic devices can be quite large. Those are AC to DC converters that allow you to take alternating current from your wall and change it into direct current that you can use for your electronic devices. So we're going to start by talking about direct current, and we'll talk more about AC and DC current later on in this class. So this is a simple DC circuit. It's called we have here a battery, an EMF source. A battery is represented by the symbol, it's two parallel lines of uneven length. So you have a larger line above a smaller line, or vice versa. The larger line represents the positive terminal of the battery, or whatever you're using, motor or generator, and the negative is represented by the smaller length. Here we have a simple switch, so I can flip it up or flip it down to connect all three of these elements together, or flip it down and remove the battery from the circuit. We have a capacitor here, represented by the capacitance of the capacitor, value C. This capacitor is drawn two parallel lines of equal length. So that's the symbol for a capacitor that we'll be using in circuits. And then resistor is this sawtoothed, jagged pattern. A resistor is just an element that resists the flow of electricity. We'll talk more about resistors later on. I just want to show you what a circuit would look like with a capacitor in it. Now, when I flip this circuit up and turn it on, if you will, the battery starts supplying charge and current to this circuit. So current I begins to flow through this circuit. And the capacitor begins to charge up. The left side of the capacitor, being attached to the positive terminal of the battery, begins to get a positive charge. The right side of the capacitor is connected to the negative terminal of the battery. You get a negative charge until a total charge of plus Q shows up on the left side of the capacitor, and total charge of minus Q shows up on the right-hand side of the capacitor. When that happens, the capacitor is charged. Remember the equation for a capacitor, the total charge on a capacitor is equal to the capacitance of that capacitor times the voltage across that capacitor. Here the voltage is just the voltage of the battery, it's E value. So this could be 12 volts, 9 volts, 6 volts, 1.5 volts, whatever. Once the capacitor is fully charged, current will stop flowing in this circuit. Now, we've stored energy. We've stored charge in that capacitor. Now, how do we use it? Well, when I flip the switch down, you can see that I've removed the battery from the circuit. Now the circuit is just this loop. So what will happen is positive charge will start to flow out of this capacitor plate across the resistor and towards the negative side of that battery, of that capacitor. So the capacitor will discharge until all of the positive charge from one battery goes back to the negative charge of the other capacitor. My apologies, I keep on saying battery. The positive terminal of this capacitor discharges to the negative terminal of the same capacitor. That will cause current to flow, I, through this circuit, when current moves through this resistor value, that resistor gives off heat, gives off light, whatever that resistor is designed to do. Here we can pretend it's a camera flash. So when we have the circuit in the upright position, we're charging the camera's capacitor. And then when we have it in the lower position, we send the stored charge through the resistor, causing the camera light to flash. Or in the example of the paddles that I used in ER situations, where the defibrillators, where you'll hear a doctor say charging, clear, and then zap the patient. Well, charging is in the upright position, where the capacitor in that defibrillator is charging up. And when they say clear and they hit the buttons, the switch gets flipped and the charge moves through those paddles, through the patient's heart, hopefully getting the heart back into appropriate rhythm. So this is how a capacitor works in a very simple circuit. And we'll be talking more about it later on when we talk about circuits. So in the beginning, current will flow in the circuit until the capacitor is fully charged. And then to use the charge in the capacitor, we flip this switch and we can discharge the capacitor. The advantage of a capacitor over a battery is a battery is a chemical process. You might remember that from a chemistry class. It's when a chemical process goes on inside a battery. Some chemical processes are reversible, giving you a rechargeable battery. Some are not, why some batteries are not rechargeable. But that chemical process occurs at a specific rate. You can't accelerate it. There's a maximum rate at which you can generate power out of a battery. A capacitor can discharge much more quickly. So you can think of a battery as slowly filling up a large bathtub of water with a slow-moving tap, and the capacitor is the bathtub can just open up the bottom and all the water rushes out. Terrible analogy, but I think it's somewhat helpful. So capacitor takes a while for the battery to charge the capacitor, but once the capacitor is charged, it can very quickly discharge. So if you need a lot of energy very quickly, a capacitor is the way to do it. So what if you need a capacitor in a circuit and you don't have the right capacitance value? Let's say you're building a circuit and it calls for a 10 microfarad capacitor and you don't have one. Well, one way you can emulate a 10 microfarad capacitor is by adding capacitors you do have in what are called series and parallel configurations. And we'll talk about that in a moment. So the first circuit configuration we're going to look at is that of a series circuit. So when you have multiple circuit elements attached together in such a way where the current or charge that flows through one element must also flow through the second element, it doesn't have a choice of branching off and going elsewhere, then we say that these circuit elements are in series. So for this simple example here, I have a battery, again, parallel, uneven length lines. Charge will flow through capacitor 1, and then through capacitor 2, and then through capacitor 3 before it goes back to the negative terminal of the battery, right? So any charge that flows through capacitor 1 can't just go back to the battery. It has to go through 2, and it has to go through capacitor 3 before coming back. So we say that these capacitor elements, or these circuit elements, are in series, a series of one after the other. So what we would like to do is there a way to simplify this circuit? So rather than having 3 capacitors of potentially different values, we can replace those 3 capacitors with a single capacitor, C sub S. So that's the capacitor, equivalent capacitor in series, C sub S, where we have a single capacitor we can plug into the circuit. Now, we're going to be solving problems in that form, but in reality, it works the opposite way, where you're asked for a capacitor of a given value, you find you don't have it, but you have some other capacitors that you can connect together to get to the capacitance value you want. So, I want to prove to you in just a moment, capacitors in series, and this series configuration, must have the same charge. And the way to think about that is, as this battery is charging up these capacitors, right, positive charge builds up on the capacitor C1. Negative charge builds up on the opposite plate, so this is charge plus Q on one plate and minus Q on the other. But where does this charge minus Q come from? Where do those electrons come from? If you look at the circuit, they don't come from the left-hand side of this capacitor plate because these plates aren't touching. So where do those electrons have to come from? They come from the left plate of capacitor 2, right? So the electrons that you have here, charge minus Q, came from this plate, which now has a net positive charge of plus Q. Well, if it has a charge of plus Q, the other plate has to be minus Q. Where did those electrons come from? Well, those electrons came from the left plate of capacitor C3. So since you remove those electrons, there's a net positive charge left of plus Q. And on the right-hand side of the plate, that is minus Q. And those electrons came from, if you will, the positive plate over here on capacitor C1. So since these plates are isolated, if you think about it, this dotted line, this dotted red line, right? Think of it as a fat H, the wire there. That's an isolated conductors. Charge can't leave those conductors. So if this plate has charge negative Q, if you have excess electrons over here on the left-hand side of this H, right, the right-hand side of capacitor plate C1, they had to have come from elsewhere on that conductor, and they came from the left plate of capacitor C2. So capacitors in series must have the same charge throughout. Since capacitors in series have to have the same charge, we can use the equation for capacitors, if you remember, Q is equal to C times V. If they all have the same charge, that means that they can't have the same voltage drop across each capacitor plate. We can add up and create the equivalent capacitance that we want using the following equation. 1 over the equivalent capacitance for a series circuit is equal to the sum of the reciprocals of the individual capacitance values. So whatever capacitance C1 is, 1 over that value, plus 1 over C2, plus 1 over C3, plus however many capacitors you have in series. And again, they have to be in series. If the circuit comes, if there's a connection here to a resistor and off, then C2 and C3 are no longer in series because current can either flow through C3 or go through the resistor. That's not what we have here though. We have these 3 circuit elements in series. So the capacitors in series, the equivalent capacitance is the reciprocal of the sum of the reciprocals of the individual capacitance values. So for example, let's pretend each of these is 10 microfarads. What is the equivalent capacitance? Well, it's 1 over 10 plus 1 over 10 plus 1 over 10. So it'll be 3/10. But it's the reciprocal. 1 over CS is the reciprocal of that. So CS is the reciprocal of 3/10, which is 10/3. 10/3 is 3.3333. So instead of using 3 10 microfarad capacitors, I can use a single 3.33 microfarad capacitor. Or again, using it reverse, if I have a circuit element that calls for a 3.3 microfarad capacitor here and I don't have it, I can use 3 10 microfarad capacitors in series to get the same result. So this is the series configuration. Let's look next at a parallel configuration. So here we're going to talk about circuit elements in parallel configuration. So a parallel configuration is one in which the charge that flows through a circuit has the choice of going through 2 or 3 or 4 or however many different circuit elements, individual elements, before coming back to the same location. So, for instance, here's a battery again. As charge flows, as we get current flowing through this circuit, that current can choose to go down either through capacitor 1 and back to the battery. It can go through capacitor 2 and back to the battery. or it can go through capacitor 3 and back to the battery. So it has the choice of going through 1, 2, or 3 before ending up back where it started. Real-world analogy would be checkout line at a grocery store, right? If you've ever been to a large Walmart or Target or any type of a grocery store that has multiple checkout lanes, most of them do nowadays, when you have your groceries, you can choose to go through lane 1 or lane 2 or lane 3, right? You don't go through lane 1 and then go back and go through lane 2. That doesn't make any sense. You choose one of the lanes and you're out the door. So parallel configurations, you go through a single circuit element and back to the same location. So, or the same destination. So you have a choice of going through either C1, C2, or C3 here. These circuit elements therefore have a parallel configuration. Now, circuit elements that are in parallel have the same potential across them. So, imagine this is a battery. Let's say this is 9 volts for the sake of argument, a 9-volt battery. That means that capacitor 1 has 9 volts between it because the top terminal of capacitor 1 is attached to the positive terminal of the battery. The bottom terminal of capacitor 1 is attached to the bottom terminal of the battery. Therefore, whatever the voltage is of the battery is the same as the voltage of this capacitor. Likewise, capacitor 2, the top and bottom terminals are also connected to the positive and negative terminals of the battery, as is the same for capacitor 3. So each of these capacitors has the same voltage, but they might have different capacitance values, right? This might be a 10 microfarad capacitor, this might be 20, this might be 30, or 1, 5, and a billion, whatever values, right? They're random. You can make them whatever you want. So these, not random, but depends on the capacitor you're using. These capacitors, therefore, the charge on each capacitor is different. In a series circuit, the charge on a capacitor was the same, the voltage on the capacitors differed. In a parallel configuration, the voltage is the same, the charge differs. So this is going to have some charge plus Q1 on one side and minus Q1. This is going to have plus Q2 and minus Q2. This is going to have plus Q3 and minus Q3. So the charge will be different, right? Same voltage times different capacitance values give you different charge values. So again, how do we create an equivalent circuit? How do we take these 3 capacitors, or 4 or 5, or however many capacitors we have in parallel, and create a single capacitor that does the same job? Well, to do that in parallel, it's easier than it is in series. The capacitance value for a parallel capacitor, capacitors in parallel, is just the sum of the individual capacitance values. So in the last example earlier, we said, what if each of these capacitors were 10 microfarads? In series, we learned that the equivalent capacitance in series would be 3.333 microfarads. Here, it's 10 microfarads plus 10 microfarads plus 10 microfarads. That's 30 microfarads. So the equivalent capacitance will be 30 microfarads. So it is important to understand this distinction between series and parallel circuit elements. And we'll talk more about this when we talk about resistors and when we talk about circuits in general.